Hello there, a great person and science interested person. So today we're going to react to another science science channel. It's PBS based and one of my absolute favorite science channels I know, and they are so great. I'm already subscribed to them, and that is why I've seen some videos of theirs, but there's a video I always wanted to watch. I haven't gotten around to watch it, and today I will watch it. And it's about electrons do not spin, which is actually something I'm gonna do research on. So yeah, perhaps question from me: how do you imagine the spin of an electron? And you might have not heard that, but if you've heard it, how do you imagine it? And that is something that we are currently working on, and yeah, because we need to know things like that to perhaps improve the understanding of what an electron spin is, because electron spins are very, very important in quantum computing, as you might imagine. And we're doing currently in Europe a lot of research in quantum computing, and also we are trying to develop programs for training new quantum workforces, and we need to find out what they can do and stuff like that, and how to teach them some skills. And this is a skill they need. So spin is quite important, and I want to see the video because I really love this channel. And yeah, please watch it perhaps first on their channel. Give them the view, not me. And I'm just gonna react to it and comment on it, what I think. But I'm sure they're gonna do a lovely job. And this is actually a field where I'm more knowledgeable than astrophysics. So I might give you some interesting insights. And yeah, there is something I want to tell you about spin, and if they don't do it, I will do it, and that's so cool, and it's so vast that theory that springs from it. And yeah, whatever. Let's just get into this. I know you think already, oh, he's talking again. Let's just see what he's got for us. This lovely guy. I'm not sure how he's called, but let's see what he has. So let's go.
Has lots of weird stuff, but there's one thing that everyone agrees that no one understands. I'm talking about quantum spin. Let's find out.
Ooh, I don't like these statements. A friend of mine who's working on the demystification of quantum physics would now say, yes, there are a lot of people, just not the layman. But yeah, it's a complicated concept. But yeah, that's a statement. Take that with a grain of salt. But I'm sure he just wants us to get into the video. I mean, I'm already in. Perhaps you are now too. Let's find out what the spin is.
How chasing this elusive little behavior of the electron led us to some of the deepest insights into the nature of the quantum
It's a
world.
property, though. It's not strictly speaking behavior. It's a property.
There's a classic demonstration done in undergraduate physics courses. The physics professor sits on a swivel stool and holds a spinning bicycle wheel. They flip the wheel over and suddenly begin to rotate on the stool. It's a demonstration of the conservation of angular momentum. The angular momentum of the wheel is changed in one direction, so the angular momentum of the professor has to increase in the other direction to leave the total angular momentum the same. Believe it or not, this is basically the same experiment. Suspend a cylinder.
So I hope you've seen this experiment. If not, if you're still in school, ask your physics teacher to do it. Every physics teacher has this setup. Or yeah, if you know it from a university class, all the better. So let's see what they do here.
Of iron from a thread and switch on a vertical magnetic field. The cylinder immediately starts rotating with a constant speed.
Yeah.
At first glance, this appears to violate conservation of angular momentum because there was nothing spinning to start with. Except there was. Or at least, there sort of was. The external magnetic field magnetized the iron, causing the electrons in the iron's outer shells to align their spins. Those electrons are acting like tiny bicycle wheels, and their shifted angular momenta is compensated by rotating the cylinder. That explanation makes sense if we imagine the...
It's not spin though. If you talk, yeah, you have to be careful here. If you see this, it's like an atom, and the atom itself and the electrons in the electron in the atom shell, they do have angular momentum and spin. So it's not spin he's talking about here. It's really angular momentum, and that's he's mixing it up here a bit. But yeah.
The electrons like spinning bicycle wheels, or like spinning anything, which might sound fine because electrons do have this property that we call spin. But there's a huge problem. Electrons are definitely not spinning like bicycle wheels, and yet they do seem to possess a very strange type of angular momentum that somehow exists without classical rotation. In fact, the spin of the electron is far more fundamental than simple rotation.
Yeah.
It's a quantum property of particles,
Yeah, okay, yeah.
like mass or the various charges.
Yeah.
But it doesn't just cause magnets to move in funny ways. It turns out that quantum spin is a manifestation of a much deeper property of particles, a property that is responsible for the structure of all matter. We'll unravel all of that over a couple of episodes, but today I want to talk about what spin really is and get a little closer to understanding this weird property of nature. The experiment with the iron cylinder is called the Einstein-de Haas effect, first performed by, well, Einstein and de Haas in 1915. It wasn't the first indication of the spin-like properties of electrons. That came from looking at the specific wavelengths of photons emitted when electrons jump between energy levels in atoms. Peter Zeeman, working with the great Heinrich Lorentz in the Netherlands, found that these energy levels tend to split when atoms are put in an external magnetic field. This Zeeman effect was explained by Lorentz himself with the ideas of classical physics. If you think of an electron as a ball of charge moving in a circle around the atom, that motion leads to a magnetic moment,
Yeah, and that's what I was talking about. I'm sorry for pausing it here. That's exactly that. You know, the electron spinning around the atom, if you take this model, which is not a quantum physical model, this is, this is Stone Age physics, so to speak, for me. Sorry, but yeah, in that model here, it's you have the rotation around the nucleus, so the core, and you have the electron that might spin itself, and you have to be careful not to confuse those two. I hope it was clear in the beginning. I think they meant the right thing, but yeah, with the bicycle thing, it's like the electron is moving around, and that makes that creates a magnetic field. In this model, I mean, it's not that way, but you can take this model. It's fine for what we want to discuss, I think. And the electron itself would spin in this model if you take this model, which does not make sense in today's physics. But yeah,
dipole magnetic field like
Yeah.
a tiny bar magnet. The different alignments
Lorentz
of the orbital
effect.
magnetic field relative to the external field turns one energy level into three. Well, sounds reasonable, but then came the anomalous Zeeman effect. In some cases, the magnetic field causes energy levels to split even further, for reasons that were, at the time, a complete mystery.
Yeah.
One explanation that sort of works is to say that each electron has its own magnetic moment. By itself, it acts like a tiny bar magnet.
Yeah.
So you have the alignment of both the orbital magnetic moment and the electron's internal moment contributing new energy levels. But for that to make sense, we really need to think of electrons as balls of spinning charge. But that
Yeah.
has huge problems.
Yeah, it
For
has.
example,
That is absolutely that you can do that. And perhaps I hope I'm not gonna go on a very long tangent now, but you can imagine it like a ball. That's completely fine, but it's not the quantum physical way to imagine it. And that's, I think, one of the hardest things in quantum physics, if you learn it, that you think of these balls that are running around some path. And I actually did a lot of research in this area and how people understand that. And many people, they can't give up this image that there is a little ball running around the path, and that's the biggest conceptual hurdle and obstacle in quantum physics. If you want to learn it, you have to let go of this image. But of course, you can't just let go, so you have to get a better image that works as well and can explain more. And that's a very big problem I face in my field of work, because we try to teach people quantum physics, and this particle image of the ball, so a particle is a literal particle of dust, so to speak. It's not something you can work with in any way nowadays, and that's problematic, because in school it makes sense. And if you look at these things, you have to always keep in mind that you are working with models. Everything you learn in a school book about things that are about the size of an atom, they are models. It's just images. And Niels Bohr, when he proposed his model, the one with the electrons spinning in different distances around the nucleus, that one is actually, he said about that, and you might think, yeah, that's how it looks. If I take a microscope, that's how it looks. No, he said, yeah, it's like poetry. I just imagined it. I just made it up and it works. I don't know. I don't think that it looks that way. I never did. It's like poetry. I just created something that made that explained things. So none of the scientists, and I've talked to a lot of quantum physicists, and I mean I'm not even working that long in this field. I mean perhaps 6 years, 3 to 6 years, and I've talked to several quantum physicists and people who try to do quantum physics education, and every single one they all say, yeah, of course it's not this image. It's not like that in reality, but these pictures suggest that. So yeah, so let's just do that. Tip for learning: if you learn something new, you can imagine things, but in every type of learning, there is a moment when you have to let go of your image. It's not the image that you want to learn, it's how it works. And if it doesn't work anymore, you have to take another image. And this is very important here. So I'm sorry, long tangent over. I can tell you more about that in the future if you're interested down the line, but yeah.
In order to produce the observed magnetic moment, they need to be spinning faster than the speed of light. This was first pointed out by the Austrian physicist Wolfgang Pauli.
Yeah,
He
great
showed
man.
that if you assume
Great
electrons
man.
have the maximum possible size given by the best measurements of the day, then their surfaces would have to be moving faster than light to give the required angular momentum. And that's assuming the electrons even have a size. As far as we know, they are point-like. They have zero size,
Yeah,
which would make the idea of classical angular momentum.
but not as far as we know right now. That's also not really true, but yeah. I mean, yes, they are point-like, but only when you measure them. That's very important. And if you say that like this, you throw out half of quantum physics already. So this is already again this perhaps this classical physics world you know that he's explaining, and there's a quantum physical world behind that. And he's only talking about this classical way all the time here. It's probably for didactical reasons, and I really like his approach, but you have to be careful there. You have to be really careful, because this property that it's a point-like thing, it's not a point in space all the time, almost never. Almost never. And that's also this picture of this point that does things. It's very bad to think about it this way, but yeah.
Even more nonsensical, Pauli rejected the idea of associating such a classical property like rotation to the electron, instead insisting on calling it classically non-describable two-valuedness. Okay,
What?
so
I didn't
electrons
know that.
aren't spinning, but somehow they act like they have angular momentum.
Yeah, by the way, if you read the old papers like from Niels Bohr or so, it's so funny. They sometimes do such stupid stuff like, yeah, it's yeah, just do that. I don't care. Just it's like, this yeah, you might know I'm from Istria. We say how will work. Yeah, if we just do this, it will just work. It's always in these times, always in the papers, because they were so creative and it just worked.
And this is how we think about quantum spin now. It's an intrinsic angular momentum that plays into the conservation of angular momentum, like in the Einstein-de Haas effect. And it also gives electrons a magnetic field. An electron's spin is an entirely quantum mechanical property,
Yeah.
and has all the weirdness you'd expect from the weirdest of theories. But before we dive into that weirdness, let me give you one more experiment that reveals the magnetic properties that result from spin.
The Stern-Gerlach.
This
Yeah,
is the
Stern-Gerlach.
Stern-Gerlach experiment.
This experiment, I would always, if you try to understand spin in its quantum properties, you should look at this experiment and several experiments that are after that came after that were based on this, and they show this incredibly cool property of spin that will make you go, what? And it will help you to understand quantum physics. So I hope they do the experiment justice here, but I think they will, because I know them. They normally do good stuff.
Proposed by Otto Stern in 1921 and performed by Walter Gerlach a year later. In it, silver atoms are fired through a magnetic field with a gradient. In this
Yeah.
example,
Gradient means like it's the way he showed it correctly. It goes apart. It's close to the top and then it goes apart.
stronger towards the North Pole above and getting weaker going down.
Yeah, okay, sorry.
A lone electron in the outer shell of the silver atoms grants those atoms a magnetic moment. That means the external magnetic field induces a force on the atoms that depends on the directions that these little magnetic moments are pointing relative to that field. Those that are perfectly aligned with the field will be deflected by the most, either up or down.
So yeah, so basically you shoot And again, this is just a model picture. It's not like that. But you shoot balls and they turn up or down depending on their spin. So if they go up, they have spin up. If they go down, they have spin down. Let's just say that. I mean, it could be the other way around, but you can distinguish particles by their spin with this experiment.
If these were classical dipole fields like actual tiny bar magnets, then the ones that were only partially aligned with the external field should be deflected by less. So, a stream of silver atoms with randomly aligned magnetic moments is sent through the magnetic field. You might expect a blur of points where the silver atoms hit the detector screen, some deflected up or down by the maximum, but most deflected somewhere in between due to all the random orientations. But that is not what's observed. Instead, the atoms hit the screen in
I'm sorry, I took it away from him. I'm so sorry. He wasn't even there yet.
only two spots,
I'm so
corresponding
sorry.
to the most extreme.
I'm so sorry. Yeah, it looks like
Let's keep
that.
going.
I'm sorry.
What if we remove the screen and bring the beam of atoms back together? Now we know that the electrons have to be aligned only up or down. Let's send them through a second set of Stern-Gerlach magnets, but now they're oriented horizontally. Classical dipoles that are at 90 degrees to the field would experience no force whatsoever. But if we put our detector screen, we see that the atoms again land in two spots, now also oriented horizontally.
Yeah. Okay, so he's going this route. I know this way of teaching. My university professor back in the day taught it like this. I think I wouldn't do it like this. You can do it, but it's not that. This is like something weird is happening. What are we gonna do? This makes no sense. I don't like this approach. This makes perfect sense, but he let out the cool property of the spin. So I hope he will do it later, because there is one central property of spin that I rarely see in these videos, and I hope he does it. I think he might do it because I know his channel. I know what he does, but I hope just. So this is the mystery. It goes up and down. They go back together, so then you turn the field and you expect, because there is no component up or down, so it will just go through, but no, it will split again. And so why is that?
So, not only do electrons have this magnetic moment without rotation, but the direction of the underlying magnetic moment is fundamentally quantum. The direction of this spin property is quantized. It can only take on specific values, and that direction depends on the direction in which you choose to measure it.
Yeah.
Here we see an example of Pauli's two-valuedness, manifesting as something like the direction of a rotation axis or the north-south pole of the magnetic dipole. But actually, this two-valuedness is far deeper than that.
Okay, again, I hope you're not annoyed by this, but the thing is, he said it again. If you imagine like a spinning ball, it makes not a lot of sense. And that's the point. You can't imagine it like that. But he's going to say that because I've seen this thumbnail. I think he shows the right, and by right I mean the current understanding of spin later on. So, but there again, you might be a bit confused, but no, you can't imagine like this ball that is spinning. So, yeah, don't take this picture into your head.
To understand
my advice,
why,
if you want to
we need
understand
to see how
this.
spin is described in quantum mechanics.
Yeah.
It was again Pauli who had the first big success here. By the mid-1920s, physicists were very excited about a brand new tool they'd been given, the Schrodinger Equation. This equation describes how quantum objects behave as evolving distributions of probability, as wave functions. It was proving amazingly successful at describing some aspects of the subatomic world, but the equation as Schrodinger first conceived it did not include spin.
Yeah, that is true. By the way, the Schrodinger equation, what it describes, that is quite easily to understand with a metaphor that is ancient, and it fits here as well in the Schrodinger equation, which I love a lot. So basic concept of quantum physics is quite easily to understand, in my opinion, if you know this metaphor. If you're interested in that, I might make a video on that or talk about this in their next video, because they said it's a series. I might do that. So yeah, just let me know if you want to know about that. But and I've never heard about it, that people use it to explain quantum physics. I do it all the time when I do Yeah, I sometimes teach students of mine if they prepare for the quantum physics oral exams, and I teach them because there's this part where they have to show that they understand it and not just calculate. And I'm mentoring them there, and I use that as the first thing I tell them, and it lights up their understanding a lot more. So yeah.
Pauli managed to fix this by forcing the wave function to have two components, motivated by this ambiguous two-valuedness of electrons. The wave function became a very strange mathematical object called a spinor, which had just been invented a decade prior.
Yeah.
And just 1 year after Pauli's
That's lucky.
discovery, Paul Dirac found his own even more complete fix of the Schrodinger equation. In this case, to make it work with Einstein's special theory of relativity, something we've discussed before. Dirac wasn't even trying to incorporate spin, but the only way the equation could be derived was using spinors. Now,
He's already going to spinors. I would have shown the experiment right now. That is so cool. And it's not the Stern-Gerlach, and it's not the Einstein magnetic turning thingy. I'm sorry. I don't know the name of that from the top of my head. It's not something that we teach in Germany that much, although I know the experiment, but yeah. So yeah, let's see where it's going. Let's see how deep he dives into mathematics now.
spinors are exceptionally weird and cool, and really deserve their own episode. But let me say a couple of things to give you a taste. They describe particles that have very strange rotation properties. For familiar objects, a rotation of 360 degrees
Yeah, okay, this
gets
is
it back
it.
to its starting point. That's also true of vectors, which are just arrows pointing in some space. But for a spinor, you need to rotate it twice, or 720 degrees, to get it back to its starting state.
Yeah, that is it. That is what I was talking about. That is the crucial thing. And that will tell you a lot of things about quantum physics and what you have to do, and why the Schrodinger equation is imaginary and stuff like that. So it's like you take an object, and normally you would just turn it around, and then it's the same object, but with spin, if you turn it around, it's just the other way around. So you have to turn it twice, so to speak, so it turns around once, which does not make sense at the first glance, but yeah, it makes sense if you take into account that it's higher dimensional. So yeah, I don't know if you know that, but quantum physics has at least, in quantum physics we talk about space as at least 4-dimensional, and this proves it, because in 3D space a rotation is 360 degrees, but if you rotate a spin, it is only, flipped. So you have to rotate it again, which shows that the spin is living, so to speak, in 4D space. And I mean space, not time, not space-time, but 4D space, real 4 spatial dimensions. And spin is living in it, so to speak. This living thing, I know some people don't like it. And that's the cool thing. And they have done this experiment, I think in 69. It's quite late when they did it. And this experiment is so mind-blowing. You just turn something by 360 degrees, and it just flips, and it's not turned around. It's so mind-blowing, and that's everything you need to know. And that's where you really start to go into quantum physics, because it's 4D. It doesn't make sense in 3D. Mathematically, you can't describe it. You have to take 4 dimensions. And that shows you that the quantum world is at least 4-dimensional. And that's so mind-blowing and so great. I hope they say this now, because I went overboard again, so yeah.
Here's an example of spinor-like behavior. If I rotate this mug without letting go, my arm gets in a twist, but a second rotation untwists me. We can also visualize this with a cube attached to nearby walls by ribbons. If we rotate the cube by 360 degrees, the cube itself is back to the starting point, but the ribbons have a twist compared to how they started. Amazingly, if we rotate another 360, not backwards but in the same direction, we get the whole system back to the original state. Another thing to notice is that the cube can rotate any number of times.
Yeah, and this is more like what I would imagine spin to be. This weird string thing, that's actually quite close to what I imagined there. Because it's not space that's distorted, but the field in the space is distorted like that. And that's so cool, and it distorts, that's spin. And this is not a 3-dimensional thing. It's a 4-dimensional thing, and that's why it looks so weird. And there's if they did this correctly, this is a stroboscopic, I think. I think it's a stroboscopic representation of a spin, which means you mapped it onto 3D. But they might have, yeah, I think this is just the notch model thingy where you still have 3D, but yeah, it's close to that.
With any number of ribbons attached, and it never gets tangled.
Yeah.
So, think of electrons as being connected to all other points in the universe by invisible strands. One rotation causes a twist, two brings it back to normal.
Yeah.
To get a little more technical, the spin or wave function has a phase that changes with orientation angle, and a 360-degree rotation pulls it out of phase compared to the starting point. To get some insight into what spin really is, think for a second not about angular momentum, but about regular or linear momentum. A particle's momentum is fundamentally connected to its position. By Noether's theorem, the invariance of the laws of motion to changes in coordinate location gives us the law of conservation of momentum. For related reasons, in quantum mechanics, position and momentum are conjugate variables, meaning you can represent a particle wave function in terms of either of these properties, and, by Heisenberg's uncertainty principle, increasing your knowledge of one means increasing the unknowability of the other. If position is the companion variable of momentum, what's the companion of angular momentum? Well, it's angular position. In other words, the orientation of the particle. So, one way to think about the angular momentum of an electron is not from classical rotation, but rather from the fact that they have a rotational degree of freedom, which leads to a conserved quantity associated with that. They have undefined orientations, but perfectly defined angular momenta. Some physicists think that spin
It's
is
a lot
more
for
physical
novices,
than
I
this.
think.
Hans Ohanian, author of one of the most used quantum textbooks, has shown that you can derive the right values of the electron spin angular momentum and magnetic moment by looking at the energy and charge currents in the so-called Dirac field. That's the quantum field surrounding the Dirac spinor, aka the electron, implying that even if the electron is point-like, its angular momentum can arise from an extended, although still tiny region. However you explain it, we have an excellent working description of how spin works.
And also, and I don't know how many people think that, but some people think that this distortion is also connected to gravity. I'm not sure how far they are in that thought train. I think that's cool idea. There is the Einstein-Cartan extension of the field equations. I think you say it like that in English. And yeah, so this distortion might actually and what you said, this, so the electron, if you measure it, it's a point. If you measure it, it's a point, and around that the spin is like distorting space a little bit. That's a theory some people have nowadays. I don't know how much it is actually a part of the science community, how many people really believe that, but it's quite an interesting thought. And yeah, if I had time, I would think about that more, but I don't, so I'm not doing that.
We say that particles described by spinors have spin quantum numbers that are half integers, half, 3 on 2, 5 on 2, etc. The electron itself has spin half, so does the proton and the neutron. Their intrinsic angular momenta can only be observed as plus or minus a half times the reduced Planck constant projected onto whichever direction you try to measure it.
Projected to. That's so important. That's as well. So if you have a 4D spin object, let's say, and you measure it, you project it into our space. And that's very interesting. So yeah, that's a very important word he just said there, the projection. Projection is so important in quantum physics.
We call these particles fermions. Particles that have integer spin, 0, 1, 2, etc., are called bosons and include the force-carrying particles like the photon, the gluon, etc. These are not described by spinors, but instead by vectors. And
by the way, I just read a paper where they created a model for the Big Bang without using spin 2 particles, so without using gravitons, which is interesting, and without supersymmetry. So yeah, there are quite some interesting things there. And it's, yeah, spin is like these bosons, fermions. That's very important stuff for today's physics, for particle physics. You have to know this if you want to go into particle physics very well, very well. So you have to know this if you're waking up at midnight and you someone points a gun at you, says I don't know, and any question about this, you have to answer it.
Behave more intuitively. A 360-degree rotation brings them back to their original state. This difference in the rotational properties of fermions and bosons.
Yeah. And you know why that is? Because you can, and that's actually something I did with a colleague of mine. We tried to combine this problem, because if you take a boson and you rotate it, it does the thing you think, it does this. It comes up the same, and a fermion doesn't. And why is that? So me and a colleague of mine, we actually, I don't know if we were the first ones to unify that, but we probably were not. I mean, come on. But we showed that with Möbius strips, actually. So I might do that one day. I might show you that it's quite consistent. So you can model these particles, bosons, and fermions with get these properties that he's describing here with the rotation of 360 and 720. You can get that by just using a paper strip. It's such a cool thing. And we just did it for to explain it to people, because this is stuff we try to explain to people, as I said. And yeah, I might show you that one day, if you want to know that. It's so cool. You can derive both of those things from just a paper strip. It's very, very easy. I mean, it's easier than what he said about, yeah, there are spinos and blah blah. I'm not trying to diminish what he said. Just this, he had a more his approach there was more like if you were already in the know. I don't know how easily it was to understand what he said. So I mean, he is right completely, but these things, if you're an expert in things like this, you tend to assume everyone else is an expert, and it's really hard to explain things to people there. And yeah, anyway, let's continue. So yeah, bosons, you can spin them, and an easy explanation for that is like you have the same property twice. So you can do that, and you can do that again, and it still stays up. So it's consistent with that idea. It's just that bosons have the special property that they don't sign change when you rotate them. So they never sign change after rotation, and the fermions do. But there is more to say about that, which I will do perhaps in another video if you like.
Results in profound differences in their behavior. It defines how they interact with each other. Bosons, for example, are able to pile up in the same quantum states, while fermions can never occupy the same state. This antisocial behavior of fermions.
And that too, I'm sorry that I interrupted here again, but that too, if you wouldn't have four-dimensional space, everything would just be goo, because bosons could theoretically live in 3D space. Fermions could not. They could not exist because you have this property with double rotation. So that means everything would not exist, because everything is just on one energy level and it's just goo. It's Bose-Einstein condensate, so to speak, everything. Nothing could ever have arisen in the universe. Such a cool thing. And from that you see that we live in 4D space, but we don't notice it.
Manifests as the Pauli exclusion principle, and is responsible for us having a periodic table, for electrons living in their own energy levels, and for matter actually having structure. It's the reason you don't fall through the floor right now.
Yeah.
But why should this obscure rotation...
I'm so sorry that I take everything away from it.
...fundamental behavior? Well, this is all part of what we call the spin statistics theorem, which we'll come back to in an episode very soon.
Ooh, I would like to see that.
Electrons aren't spinning. They're doing something far more interesting. The thing we call spin is a clue to the structure of matter, and maybe to the structure of reality itself, through these things that we call spinners, strange little knots in the subatomic fabric.
And that's also exactly right. The knots are what is actually currently developed by Louis Kaufmann and people like him. Great mind, such a great mathematician. He does knot theory, and you can use knot theory actually to describe a lot of properties. And a colleague of mine and me, we actually also included entanglement and stuff like that in just this knot theoretic approach. And it's quite something. Perhaps it's just a nice little thing to do, but it's so interesting that that knots in a way, are what describes all the stuff that you think are little balls flying around. It's just not structures, a mapping, and whatever.
of spacetime. Last time we talked about the connection between quantum entanglement and entropy. This was a heady topic to say the least, but you guys had such incredibly insightful comments and questions. Joseph Paul Duffy asked whether entropy is an illusion created by our observation of isolated components within a larger entangled system. Well, the answer is that entropy is sort of relative. It's high or low depending on context. The air in a room may be perfectly mixed and so considered high entropy, but if that room is warm compared to a cold environment outside, then the total room plus environment is at a relatively low entropy compared to the maximum if you open the doors and let the temperature equalize. Von Neumann entropy is different to thermodynamic entropy in that it represents the information contained in the system.
It's funny, I'm actually currently writing a paper on that with a colleague of mine.
And extractable in principle, versus information that's lost to the system by entanglement with the environment. On the other hand, classical or thermodynamic entropy represents information that is hidden beneath the crude properties of the system.
And just a little tease, I'm so sorry that I'm interrupting him all the time. Great guy. Entropy alone would not really explain how things are stable, because quantum entropy very easily gets maxed, so to speak, in information. So the question is, why doesn't it just, and it's there and nothing changes ever again, because entropy is makes. So there's complexity, which is a new field of, and not, I mean, it's something that people discuss a lot nowadays, because that's something that comes together with entropy there. And yeah.
But may in principle be extracted. And yet, von Neumann entropy has a similar contextual nature. If your system has no entanglement with the environment, then its von Neumann entropy is zero. But if you consider a subsystem within that system, then the entropy rises. Randomated asks the following. If entropy only increases over time, which implies it was at its minimum at the Big Bang, does that mean there was no quantum entanglement at the Big Bang?
Interesting question.
To answer this, we need to know why entropy is so low at the Big Bang, and that's one of the central mysteries of the universe. But I'll give it a shot anyway. So we can't really talk about the t=0 beginning of time, because that moment is lost in our ignorance about quantum gravity and inflation. And
yeah, exactly. And there's a lot I could say about that, because I recently read a paper about a quantum gravitational model of the Big Bang, which is a great paper. Yeah, but that's really, we don't know anything about point zero, because point zero probably doesn't even make sense, because time might be quantized, which I think, but I think there are other theories that might work without it, as far as I know, but correct me if I'm wrong. And yeah, so it's like, where do we come from? There are some things that we can't answer here, but let's say what he does. I've got a theory, but let's see what he does.
And whatever other crazy theory we haven't figured out yet. But what we do know is that at some very, very small amount of time after t=0, the universe was extremely compact, which meant hot and dense, and was also extremely smooth. The compact part is where the low entropy comes from. The gravitational degrees of freedom were almost entirely unoccupied. On the other hand, the extreme smoothness meant that the entropy associated with matter was extremely high. Energy was spread out, as it could get, between all of the particles and the different ways they could move. The low gravitational entropy massively outweighed the matter entropy, so entropy was low. That smoothness, though, seems to suggest that the particles of the early universe were already entangled, otherwise how did they spread out their energy? Chris Hansen makes the same point.
Oh yeah, okay.
Asking if the
Let me read that first. Yeah. And this is just a I don't know, do you say like a spitball theory? I don't know, just out there. Something I've thought about but never really. Also, I haven't thought about that much, so it's more like a quite funny idea. And some people believe that. I've read people who believe it, that actually we are caused by a black hole. creating in another precursor universe. So that means, yeah, that might explain that with the maximum entanglement. Because it's from a singularity, so to speak, which is obviously entangled, and then, yeah. But I'm not so sure about that. But yeah, correct me if I'm wrong, but yeah.
Conditions of the Big Bang meant everything started out entangled. Well, you'd think so, but that's not necessarily the case. Remember that von Neumann entropy is relative to the system you're talking about, and so is entanglement. Let's say you have a bunch of particles that are not entangled with each other, but are entangled with another bunch of particles somewhere else. If you ignore those other particles, then it seems like there's no entanglement in the particles of the first system, and yet those particles may have correlated thermodynamic properties due to their mutual connection to the outside. In the early universe, the extreme expansion of cosmic inflation may have permanently separated entangled regions, but left those regions with internal thermal equilibrium, which does not require maximal entanglement within those regions themselves.
Yeah, it's the problem with the expansion that was the one of the first expansions. I wanted to say something else. What was it? Yeah, entangled particles. Actually, I'm not sure how much this is a model or not, but if you have two particles entangled, they are the same object, so to speak. Can't say they are particles anymore. They are not two particles anymore. They are one object that's the entangled object of particles before AB before. You know, that something like that. That's so you have to be careful there. I might watch a video on entanglement of theirs, say, because they're good, and he's talking a lot of more, I think, deeper stuff than I would have expected, which I like, but I don't know if you get everything of this. You might, I can't really say, but that's something I would like to talk about as well, perhaps. But yeah.
In other words, the universe or our patch of it may have started out unentangled and at low entropy, even if it was at thermal equilibrium. Lincoln Mwangi also dropped some knowledge, informing us that the cloud is actually named after Dr. Shannon, the founder of the field of information theory. Now, as with many of these things, the word has been corrupted over time and is now routinely mispronounced. This is very disrespectful, and I intend to write a series of op-eds to correct the matter right after we upload this video.
Yeah, I think that was it. So, anyway, that was a very great video. A lot of stuff. I would have done some things in another order, and I don't know if they talk about this fundamental idea. And he didn't really go into the four-dimensional stuff, which is the crucial step. That's the crucial step. You have to understand that quantum physical mathematics describes a world of at least four spatial, not three, as you might know from your everyday life. And that's the core, in my mind. That's the core. And if you understand that, then you are quite a step closer. And you can explain a lot of things then, because you can explain the spin, because you can explain that bosons and fermions, so particles with integer spin and half integer spin, are different with rotations, because with 4D space you can explain it, you can't explain it with 3D space, you just can't. And the Schrodinger equation is actually imaginary, and that means it's it gives a hint to something there, the higher dimensionness, so to speak. Yeah. Anyway, I really like the videos. As I said, he goes quite deeply into stuff. I really hope I did not bore you with this things I said. You know, I just react to this. This was a topic where I'm quite versed. I talked about some theories I know of that might be rubbish, and in 20 years we'll laugh at them, but yeah. And yeah, so if I would have to tell you what to take from this video, spin is not something like a ball that's spinning, makes no sense, and I hope that you consider thinking about if electrons really are little balls, if you still think that, which you might. I mean, it's fine. I did so through my studies until I graduated in the end, and I still thought it. And when I did my PhD years, I actually learned how it really was, and with really was is how people nowadays think about it. Yeah, so no little spinning particles, it's just, property of an electron if you measure it. If you measure it, it has this property, and in magnetic fields, it's quantized, like you see half a spin up, half a spin down, nothing else, not 0.568 spin up, down, something like that, nothing like that, you don't see that. And yeah, so there's this modeling with strips is actually quite powerful. So perhaps if you're interested what I currently do, and it's not my main focus, it's just something me and a friend and supervisor of mine are doing by the side, so to speak. And it's if you know, quantum physics is currently expressed by algebra and analysis. All that, I hope those are the two English names, and we're working on a topological expression there. And there are other people, of course, who've done a lot of work there, so we don't really do that much new. We just try to make it more graspable with cool or sensible pictures and models. I actually, yeah, part of my PhD thesis was actually 3D printed models for spins. That was quite fun. I did that. I did that during my master's thesis as well. It was my first contact, so to speak, with education, physics education, quantum physics, and I modeled electrons in an atom, how we now understand them with 3D printing, and also spins. So that's what I do, in part. I mean, as I said in the beginning, I mostly focus on how you understand things, and the thing I know most about how people tend to understand and not understand it is quantum physics, because I've done a lot of research in that, and I know many colleagues who've done even more research. And yeah, anyway, I think this has gone on for long enough. I hope you had some fun. Yeah, post your questions in the comment section, and if you have other suggestions, I might do next week entanglement if I find a good video, or I will continue this series. I might also do that. Let me know what you want. Yeah, and if you like this, consider liking, subscribing. I do this stuff. I try to do it once a week. I might not be able to do it every week. I also do sci-fi, horror. That's where I started, and yeah. Anyway, I hope you have a very great day. Take care of yourself. Bye.